Hello everyone, welcome to Senior Flexonics Pathways Division seminars on expansion joints. Today we'll be introducing you to expansion joints, particularly metal joints, and some of the considerations and concerns on how to select them. At the very basic, simplest level, you might be asking, why do I need an expansion joint? Well, I prepared this slide to demonstrate how pipe thermally expands when you heat or cool it. If we were to take 100 feet of stainless steel pipe and heat it to 1400 degrees, that pipe would get almost 17 inches longer. Contrastly, if we were to cool it down to minus 150 degrees Fahrenheit in the cryogenic service, that pipe would shrink 2¼ inches. And so this thermal growth has to be considered when designing and laying out piping systems. Now, there are a number of ways to absorb thermal growth. Probably the most common is the pipe loop. We've all seen them, we've all used them. They're rigid pipe and can absorb a moderate amount of movement. Now, one of the upsides of the pipe loop is that you do have increased pumping costs and friction in the system due to the loops. However, they are reasonably inexpensive. Next type of method for absorbing thermal growth is fabric expansion joints. Fabric expansion joints have a gas seal membrane that's bolted between two frames and can absorb movement in any direction or axes. The belt itself generally falls into two families of material: the rubber-based materials of typically Viton, or the new fluoroelastomers and fiberglass reinforced belts. But both of them have a probably maximum operating range of 400 degrees belt temperature. However, they can be used in higher temperature services by adding insulation, as shown in this graph. And so we have 1600 degree media temperatures operating with fabric belts by adding the insulation to assure that the gas seal membrane is operating below 400 degrees. Now, fabric expansion joints generally are limited to less than about 3 or 4 psi, and so you'll see them normally in a flue gas or off-gas system. Also, fabric expansion joints are not 100% gas tight. Our group likes to say that there will be some off-gassing through the bolted connection, so we can't guarantee 100% sealing. If this is a problem, you might want to consider a different type of expansion joint. Then the next type is rubber. Now, I'm not a rubber expert, so I won't go into too much depth, but generally here again, their temperature is limited, and then also the pressure is limited, and there's a size differential in cost. They will be relatively inexpensive up to where their standard tooling stops. And in the larger diameters, you're talking about hand-wrapped rubber, which makes them very expensive due to the labor-intensive action of actually making the belt or the joint by hand. Next type of joint to talk about is slip joints. This is simply a sliding mechanical seal and can take very large amounts of axial movement. It was the expansion joint of choice before the metal convoluted bellows came along. Biggest problem with a slip joint is the mechanical seal. That requires maintenance. Now, I think we've all seen a picture of New York City late at night, and our hero is walking down a dark back alley, and there's steam coming out of a manhole. Well, what most people don't know is New York City has one of the largest steam distribution systems in the world. The steam distribution system uses slip joints, and they're not so great on maintenance and have been known to postpone it, and as a result they have leaking slip joints in New York City and steam coming out of those manholes. So the next time you see a movie with steam coming out of a manhole in New York City, you can go, I know why, because it's of these joints. The last type of joint or competing product I'll talk about is flex hoses. Here again, I'm not an expert, basically limited to small diameter, can absorb a fair amount of movement in any direction, and might be a possible solution in the small diameter ranges. What we're here today to talk about is Metal Bellows. That's a convoluted piece of sheet metal, generally in the range of about 15 thousandths to 75 thousandths of an inch. Now, there are specialty products for the steel mills and sulfuric acid that can get you up to 3/16 or a quarter, but they're not convoluted bellows, and fairly not typical and high, or very expensive. Anyway, we can make a bellows element out of any material that can be rolled, welded, and formed. Our bottom of the line vanilla grade material is a stainless steel type 304, and from that we can move all the way through the austenitic stainless steel range into the high nickel ranges with an Inco 625 or 800H, or as I say, any material that can be rolled and welded. And here we have a movie of what most people think is the typical movement of an expansion joint, which is axial. Axial movement will compress each convolution evenly, and we can either actually compress or extend the expansion joint. Axial movement, here again, all the cons move evenly. Compression is limited by bottoming out. That's when the bellows actually the convolution shoulders actually start to touch each other. Once that happens, the movement is not predictable, and you can get stress concentrations that could cause early premature failure. Extension is generally limited by con, instability, or squirm. The more you stretch it out, the more it becomes unstable and wants to squirm on us, and I'll have some pretty gross pictures here later on. Okay, angulation. Here we have a movie showing angulation. That's a fanning effect or rotation about the center line of the expansion joint. Angulation in a piping system is relatively rare. However, with an expansion joint, when you use two as a universal, each bellows will angulate to absorb lateral movement. Angular movement is, again, a fanning shape. You can see where we have a center radius and it fans across to form the angulation. Here again, we're limited by bottoming out on the bottom of the joint where the cons actually start to touch. And it has a fairly soft reaction, and that's why we like to use them in tied universals and hinge and gimbals. It's relatively rare. We generally try to limit the amount of angulation that each bellows takes to 5 degrees. The reason for that is because after 5 degrees, and we're actually above 10 degrees, the bellow no longer operates as an expansion joint and starts to operate as an elbow. Here we have a short movie that shows how an expansion joint laterally deflects. You can see with a single bellows element, we're actually shearing the bellows itself, and so lateral movement on a single bellows is relatively limited. If you take a look at our catalog, we have published rated lateral movements for single expansion joints, and there's not a whole lot of movement capacity. And we generate fairly high loads. It's a reverse fan, so it starts to fan this direction on the left side and then reverts back on the right. And so you get a double fanning of the convolutions. We say up to 1 inch capacity. Here again, you probably should check the catalog because we do have some joints that can take more or less movement. We're limited by bottoming out in the compressive mode and then instability on the extensive mode, similar to the other types of movements. And if a single bellows doesn't give you enough movement capacity or a soft enough reaction, you can go to a universal expansion joint. Here we have a universal in the bottom picture. The way a universal joint would work is by angular rotation of the left and right bellows. So here in this movie we see how two bellows elements would act together to angulate and absorb a lateral movement. Here again, we want to keep the angulation of each bellows to below 5 degrees and definitely below 10 degrees. Last type of movement I want to talk about today is torsion. Torsion is the actual twisting of the metal bellows by the pipe system. And there is a significant problem, which is torsional instability. And as a result, we generally recommend not to design your system to have torsion on a metal bellows. You get a very high spring force, and instability is our primary concern. Our catalog does, however, have published rated torsional angulations and spring rates. When I first joined Pathway, one of the first projects that I was ever assigned was a research program into torsion. And we designed a test fixture with hydraulic actuators and instrumentation for recording strain gauge information. And the day of the test arrived, we pressurized the bellows, and I was just taking the slack out of the actuators and running them up to take up tension, and the bellows went into torsional squirm. And it was that low. So as a result of other testing, and we went on to do successful tests, but we were all amazed at how low the torsional squirm occurred. We have formulas for evaluating torsion, but in general we would recommend not using a metal bellows in a torsional application. Squirm. Out of play, or there are two types of squirm. What we're showing you here is column squirm, where the bellows actually wants to pop out. And it's generally caused by the bellows being too soft for the pressure and conditions that it's been placed in. Either too many cons or too high a pressure. And here is a bellows that squirmed. At the time when I took this picture, this was a 150-pound steam line. Plant engineer was asking me how long I thought it would last. My only thought was whether I should walk away or run away. Okay, but it never lost pressure, and they were able to shut the line down successfully and replace the expansion joint. Next type of squirm is in-plane squirm, where the convolutions will take on this wavy appearance. That's where this occurs when the convolution height is too high for the given pressure, and the convolution will actually start to become unstable. It's pressure related, and you will only see it when the bellows is under pressure. So if the bellows is insulated or has a heavy cover, you'll probably never see this because you'd have to take that off to see it under pressure. And the problem is that when you come down, the pressure will, or the convolutions will revert back to the neutral position or the normal position. And that will continue, but each cycle, the amount of instability in the convolution will increase to the point where you'll ratchet up and form a inflection point on the con. You can see right here the dimple in this convolution. Now that dimple will continue to get worse and worse until you have a failure at that point. In-plane squirm was not covered by the codes until fairly recently. I believe that came out in the 90s. And so there probably are a lot of bellows out there that have in-plane squirm problems that nobody really knew about. We now have formulas for evaluating that and preventing it from occurring in service. But it is something that we always check for when we're looking at an expansion joint. Okay, next segment is on nomenclature. What are the words? Here we have a typical cross-section of a bellows, and we have the convolution, which has a root and a crest, a sidewall, and if you have a multi-ply bellows, we'd have inner ply and outer ply. We'd have a tangent point. That's where the convolution rolls into a straight tube, and then it rolls along the cuff to the attachment point. An expansion joint is an entire assembly. Okay, it consists of bellows elements, external hardware, if any, weld ends, and accessories. The bellows is the actual convoluted portion. Now, in future seminars, we will be talking a lot about these additional components. But here we have a cross-section of probably one of the more complex expansion joints, where we have an internal liner, an external cover, root rings, equalizing rings, tie rods, limit rods, lugs, gussets, a whole variety of different components that you can add to an expansion joint. But the bellows itself is that convoluted portion. Material selection is the next topic when considering expansion joints. No expansion joint manufacturer will select a Bellows material for you. That's because we don't know enough about your system, the media, how corrosive or abrasive it might be, and so we have to rely on your expertise and knowledge. We can guide you and say, give you recommendations or suggestions of what's been used in that application in the past, but it's inherently your responsibility to select the material. If you're not comfortable with that, we can give you end manufacturers of materials and metallurgists to talk to and talk about the selection of Bellows material. Probably the most common failure mode for Bellows elements in the petrochemical system is corrosion. Now, most people will think fatigue would be the most common. However, it's not, simply because you do not cycle your plant enough to induce sufficient fatigue stresses in the Bellows element to allow it to fatigue failure. We define one cycle as cold to full operating temperature back to cold. So it's fairly common to have a turnaround or a thermal cycle once every 4 or 5 years. But we're designing those Bellows elements for 2,000 cycles. And so you can see how you would never get to the fatigue limits on the Bellows element. And therefore, fatigue is not that common a failure mode. But the only time you're going to see it is where you have vibration or some sort of batch operation where you're cycling the line every 3-4 hours or something along that line. But for normal operational start to stop cycles, you don't flex it enough to induce fatigue. The most common failure mode is corrosion. And of that corrosion, stress corrosion cracking of austenitic stainless steels due to chlorides is probably the most common. Okay, we also get high temperature sulfurous gas corrosion due to caustics. Okay, so we would look to the Bellows elements to resist this type of failure mode. And corrosion is directly related to temperature. If we can get the bellows operating hot enough that we don't get condensate on the bellows, i.e. above, say, 300 to 400 degrees, we can eliminate corrosion. Okay, and eliminate the number one failure method for bellows. Carbon precipitation is something that happens at very high temperatures, say above about 950 degrees. That will occur in your austenitic stainless steels. We do have an embrittlement phase for the high nickel materials that also operates in the creep range. And so for that reason, we generally like to see the bellows operating temperature below about 950 to 900 degrees. So if you can get your bellows operating between 400 and 900 degrees, there's no reason why it shouldn't last for 30 years. Squirm and rupture are the next failure mode, and that generally happens as a result of upset in the line and overpressurization of the bellows. And then I've already talked about fatigue and vibration. So here are a few of the materials, a limited list of what we can make bellows elements out of. The 304 or garden variety. 316 you might select if you needed a little bit more corrosion protection. 321 and 304 and the H series are for higher temperature applications. And so that's the austenitic steel family range. On the right side we have our nickel families of materials, the Manel 400, 600. In there you'll see Inco 625 LCF. That's becoming kind of a de facto standard in the refining industry, simply because that is a specialized blend of material developed specifically for bellows. The LCF stands for low cycle fatigue. And it has very good strength, corrosion resistance, and material properties for the refining industry. Now, if you need a very high temperature, the Inco 800, 800 HT are the materials of choice. As expansion joint manufacturers, we have a number of codes that we must comply with. The actual design of the bellows element is governed by EJMA, or the Expansion Joint Manufacturers Association. This organization is a collection of manufacturers that have gotten together, pooled their information to form one standard code. Now, the actual code is the result of the Anderson studies for NASA, and they published a study about this thick. Well, the Manufacturers Association took the Anderson studies and condensed it down to something about this thick, including design formulas and standards. It is a regular, Pathway is a founding member of EDGMA, and we also are a regular attendee nowadays. And so that would be where you would go to get your Bellows design standard. Now, depending on the customer and what application we're working with, we can also design to the ASME Section 8 boiler code. It has a mandatory appendices on expansion joints. B31.3 for refining has a mandatory appendix for expansion joints. Both of the Section 8 and 31.3 codes have special requirements, but then basically refer back to EDGMA for the nitty-gritty details. B31.3 for the power generation code has no mandatory appendices and really does not mention expansion joints at all. If you get anything out of this series of seminars, I hope it's a clear understanding of pressure thrust, because it can affect your career negatively if you do not understand it. Also, it will drive all further discussions on types of joints and how to use them. Pressure thrust is defined as the longitudinal force generated in a piping system as a result of system pressure. The magnitude is equal to the cross-sectional area of the ID of the pipe times the operating pressure of the pipe. So, for example, a 48-inch diameter pipe operating at 300 psi will generate 691,000 pounds of longitudinal pressure thrust. Pretty huge load that we sometimes tend to forget about. And the reason for that is illustrated here with my Coke can moving. You can see as the pressure increases, we get two bulging areas, one in the barrel and the other on the ends. Now let's take a look at what's causing that bulging. The bulging in the barrel is actually the hoop stress. Theoretically, that stress is equal to the pressure times the radius divided by T, or the thickness. Okay, it is what the code minimum wall thickness calculations are based on. The longitudinal stress, which causes the bulge at the end of our can, theoretical stress in the longitudinal direction is PR over 2T. So you can see the theoretical stress in longitudinally is always going to be 1/2 of the hoop stress. That's why in all of our codes for non-destructive examination of welds, they are very concerned about the longitudinal weld, but they hardly ever say anything about circumferential welds. Now in a piping system, what's happening is that pressure thrust is developing at the elbows. It's transmitted in tension down the pipe and cancels with an equal and opposite pressure thrust on the other side. And since it is tension, everything balances, and it's a wonderful world. That is until you put an expansion joint into your piping system. That's like introducing a spring into our Coke can. And here you see a movie of what happens. As the pressure increases, it's going to put the pressure thrust on the ends of the can are going to tend to extend or elongate the Bellows element. So as a result, in order to restrain this pressure thrust, we have to add main thrust anchors at each elbow up or downstream of the expansion joint. Now because of the magnitude of the pressure thrust, normally we don't see unrestrained expansion joints in high pressure systems. We would have to go to what's called a restrained expansion joint, either tied, hinge, or gimbal. Here's a pressure thrust restrained system where we would put main anchors at each elbow up and downstream. I'd like to conclude this little segment with a story. We sold a contractor the cheapest product we make, this flange, Bellows flange. He didn't want to spend a whole lot of money. We quoted it, put the pressure thrust on the drawing. We got the order. We put the pressure thrust on the production drawing, and we shipped it, and we thought that was the end of it. Until about 3 months later, I got a call, And it's the contractor saying, "What's wrong with your expansion joint?" And I said, "What are you talking about?" And he said, "Every time I try to pressurize it, it grows." And I said, "Please explain your system." And he had 3 tanks with a header line. Each line was 14-inch diameter, and he was doing a proof test on the system to 175 psi. And he said every time the pressure went up, our expansion joints were starting to grow. Well, a quick calc showed that each of those lines had 31,000 pounds of pressure thrust for a total of 93,000 pounds of force. And I said, "I'm sorry, but you're going to have to shut the test down." And he said, "Oh, I can't do that. You know, I've got my boss and inspectors and plant end user people. I have to finish this test." And I said, "Well, you know, there's nothing I can do for you. You know, there's no way, you know, the expansion joints are going to restrain that pressure thrust. You know, the only way is to find something that can restrain that force." And he said, "Well, how about a bulldozer?" And I said, "Can you get to it?" He said, "Yeah." And so here's a bulldozer acting as a main thrust block. You can see the bellows element, the middle one, there on the right-hand side of the picture. And he rolled a bulldozer up to act as a main thrust anchor so he could get through the proof test. Here's another shot of the bulldozer acting as a thrust anchor. You can see all the chains that he broke wrapped around the header trying to restrain that force. And if you ever were curious about what a bellows element looked like when it's been reformed by a bulldozer, here it is. And the amazing thing about this picture is that those bellows elements never lost pressure, even though they were severely mistreated. It was always a proud point in my life. As a result of this little experience, people like to say that shadow there is what's left of the contractor that designed the system because he forgot pressure thrust or didn't know about it. The end solution with this was to replace the joints with pressure balanced joints. Anyway, that concludes my little demonstration on pressure thrust. Like I say, it'll be used a number of times throughout these seminars because it does drive the selection of types of joints and how to use the expansion joints. So I thank you for attending our session, and hopefully we'll see you again in the next one. Thank you very much, and goodbye.